dendrocyte from the central nervous system posted at the bottom, and I told y'all just ignore it. This just made a better slide because it had more detail. So we covered everything. We covered dendrites that, we covered the fact that the initial segment right here coming out of the cell body is actually where it's the site of generation of propagated electrical signals. Okay, so this is where we get to actually measure the initiation of the electrical signal. Okay, and we talked about Schwann cells and myelin. Obviously, there are these little skip areas in between the Schwann cells and their myelin plasma membrane, and those are called nodes of Ranvier. Okay, it's an important structural term. The physiological importance of it we will talk about toward the end of the chapter. Okay, but the node of Ranvier is basically a very short segment of the axon that is unmyelinated. Okay, so I think I also mentioned last time that myelination acts as insulation. Okay, so that it speeds nerve signal conduction. All right, it's like a coating on the nerve that speeds the conduction of the signal, but it's also very important in nerve regeneration. And again, we're talking about the peripheral nervous system. So if you have damage to a peripheral nerve, there is a chance of getting some regrowth, some regeneration, and the myelination of those. In other words, if there are Schwann cells around, you stand a lot better chance of being able to have that nerve repair itself, okay, versus if the Schwann cells have been destroyed. So at the end of, at the axon, it's called the axon terminal, and it branches, and this stylized thing is just my attempt at showing you that this is where the next neuron begins, okay? So the synapse is actually a space where one axon terminal ends and the next neuron begins, okay? And the importance of the synapse is that there's a great deal that happens in modifying the signal as it it can be slowed down, it can be sped up. New signal transduction pathways can be activated. So there's a lot of alteration in this area that can affect the electrical and the chemical activity of the next neuron. Okay. Question?
So what were the node of Ranvier, like what's the importance of them?
We'll get to it at the end of the chapter, okay? But basically they help to, just to let you know, they greatly speed the conduction of the nerve impulses, the electrical impulses, okay? And I'll show you how they do that. But they speed it beyond just the insulation of the myelin. Okay, you're coming to this class without a lot of anatomy, and we're going to treat this slide, we're not going to go into it in depth, but it actually is a very good reference slide, and it's very important. But what I really want you to see is that it's a schematic that divides the peripheral nervous system, puts the peripheral nervous system out here, and puts the central nervous system here. Okay, now central nervous system is defined as the brain and spinal cord. Okay, so one if you don't already have the terms down, the terms afferent and efferent, okay, are very important. And if you mix them up, afferent is the direction that the signal is going toward the central nervous system, okay? And it comes from the same root as the word affable, okay? Affable, like likable. So the signal sort of likes flowing toward, okay? It's toward. Now this can be a neuron, but it can also, it could be anything coming and going out of a cell, all right? Or out of a tissue or out of an organ. And efferent suggests exiting, okay? Efferent is an exit away from. Okay, so what we basically have is these nerves that are coming out of our brain and spinal cord. Some of these are mixed together, but most of them are divided into physiologic categories of sensory and motor, okay? So you would have a sensory receptor over here. It could be somatic, okay, which is in the musculoskeletal system or in the nerves or skin. It could be visceral, sensory receptors in the internal organs, such as ones that give you a stomach ache when you eat too much, or you know that feeling of bloating or distension that we can feel in our digestive tract. And then the special senses are your eyes, ears, nose, taste, and we're going to do a sensory lab this semester. So these are specialized receptors. We don't have time to go into any more detail, but the point is that they gather information, okay, that is transmitted toward afferent, toward the central nervous system, where it gets interpreted in the brain and spinal cord, okay?
You said somatic was like in your skin and stuff? What did you say?
Somatic means body. So yeah, it would be skin, skeletal muscle. I said musculoskeletal. I don't know about specifically bone, whether that's considered visceral, but somatic is more body, visceral is more organs, okay? We don't have to get, it's incredibly complicated. And you'll see one day how complicated this is. So sending signals this way, okay? I'm not gonna go into, we used to go into this about where the cell body's located. The dorsal root ganglia are along the spinal column. Those are important clinically because that's where the pain management people inject the ganglia. They inject these collections of nerve bodies with anesthetics to help chronic pain, you know, without, and they can actually do a block where they can actually make that whole area numb without putting the patient to sleep. So, but all you really need to know is you start with sensory, goes this way, afferent, and then the other part, the other major limb, of course, is the motor side of the nervous system. Interestingly, the cell body of the motor side is in the central nervous system, okay? So the cell body of all of the nerves that innervate your muscles are in the brain and spinal cord, and they stretch beyond that. So that's a single cell, that's a single axon that goes from your spinal cord to your toe, say. So some neurons are quite long, okay, but there's still only one cell, okay, because the cell body's in this central nervous system, and it extends to whatever motor, I guess I neglected to say, a ganglia is simply a collection of cell bodies, okay? So, but the take-home message is that you've got a muscle that you want to move, a gland that you want to be activated, or another neuron, okay? So that's the efferent pathway. That's the information coming out of the central nervous system, okay? Just for completeness, you ought to at least have heard, and maybe in, if you took comparative, y'all went into this a little bit, but this includes the autonomic nervous system. When you hear autonomic, think automatic, okay? It's like, these are the functions of the body that run without us thinking about it and without our concentrating or willing it to happen, okay? So it's unconscious and automatic. So these would be things like the innervation for our breathing, for our heart rate, sweat glands, all of the digestive functions. We don't sit here and concentrate or make sure that our food goes down and gets digested properly. That's all automatic. So, so this part of this efferent part includes not only motor, voluntary motor information, but it also includes the automatic or autonomic part of the nervous system, okay? And it has three major components. Just learn them right now. The sympathetic system, the parasympathetic system, and the enteric, okay? We'll get a little bit more into sympathetic and parasympathetic when we do cardiovascular. But basically, these are both autonomic, but they tend to operate in opposition to each other. And when you have two systems that operate in opposition to each other, you get some fine-tuning, okay? Enteric suggests that's the part of your autonomic nervous system that innervates the gut. So I have this interesting statistic at the bottom that the proportions of these, okay, for every afferent neuron, okay, you have about 10 efferents, okay? For every afferent, you have about 10 efferents. But for every afferent, you have about 200,000 interneurons in the brain, okay? So the pathways that connect and cross-connect and talk to other pathways in the brain especially is huge. I mean, for every one of these, you have equivalent of 200,000 of these that are in the brain, okay? Mostly brain, some spinal cord. And this is 1 to 10. This slide on glial cells we're going to skip. Also, this slide on injury, you might find it interesting to read, but we're going to skip. So now we're going to the resting membrane potential. Okay, so this is very similar to that one slide I showed you in chapter 4, that we had an intact, unstimulated cell. If you remember, it had a nucleus, and And basically, I told you that cells tend to have negative charges that accumulate along the inside of the plasma membrane, and positive charges that tend to accumulate on the outside of the cell membrane. And these are very, very weak, okay? But we can measure them. And if we stick a little tiny microelectrode into that cell, we can use a voltmeter, or physiologists call it a potentiometer because they're such small. They're in millivolts, they're not volts. So it can also be called a potentiometer, the equipment. And it basically measures the difference across the membrane, okay? So you get a number, but you have to understand that that number represents an electrical difference, okay, between inside and outside, okay? So, what the bottom graph is showing you is that basically where you see the little asterisk is when they turn on the potentiometer, okay? So you're getting a reading of 0 because you haven't started your measurements yet, okay? And then when you actually record the difference, what you find is a result of minus 70 millivolts. Minus 70 millivolts, okay? That is the resting membrane potential for neurons. Okay? So there's a difference of minus 70 millivolts, okay? With the minus basically being here in neurons. That is their resting membrane potential. So just sitting there, that's the electrical difference across their plasma membrane. Okay, so how does this get created? Oh, the other thing I wanted to bring up real quick is when we're looking at the creation of these charges. Obviously, this is a cell, so it has a semi-permeable membrane, right? It's permeable to some things more than others, okay? So you go back to your fixed equation we talked about where J was net flux, and I told you didn't have to memorize the equation, but basically those are the factors that are going to influence this number, okay? So the permeability of the membrane, the solubility of any ions trying to cross it, the charge, the temperature of the system, okay? The mass of the ions or molecules trying to cross, all of that stuff having to do with permeability of membranes directly influences the resting membrane potential that we end up with. And we end up with one in neurons, and we end up with a different one in other cells, okay? And we had also that concentration in and concentration out, the difference of the two. That fix principle can be applied to what we're doing here, okay? So what creates this membrane potential? Well, because there are so many different ions moving around, and there's so much going around, that we basically need to start with kind of a hypothetical situation, okay? Just to start understanding and explaining what's going on. So we're going to start, I call it a hypothetical in vitro. So in vitro means, in the lab, in the dish, outside the body. In vivo means in the body, okay? So we're going to start with just one ion. Again, just for explanation purposes, we're going to start with potassium, okay? And basically, we're going to start with a situation where we have two compartments that correspond to the extracellular and intracellular compartments, okay? And we're going to start with a situation where all channels are closed, which never happens in real life, okay? But in our example, all channels are closed. We have the same concentration of sodium and potassium on either side, okay? And the charges are equal, okay? The valence of the ions is equal, is the same, okay? So we kind of start with this fake scenario and we say, you know, everything, this is the beginning, where we have closed channels, same charge, same concentration, okay? And as a first step in understanding, we see what would happen if the channels opened, okay? And again, these are just potassium channels, okay? These are just potassium channels. The sodium channels stay closed, so sodium doesn't go anywhere. Potassium goes through its channel, okay? Let's see, remember that we said that extracellular, that the bulk of the sodium was in the extracellular fluid. Remember, it was 145 was the number, and that, so sodium is high outside and potassium is high inside. So there's a natural concentration gradient when you open this channel. You've got a bunch of potassium on this side, and you have relatively little on the outside, so it's going to flow down its concentration gradient, okay? So that's basically what is happening there, and it will continue to flow, okay? And it's simple diffusion, okay? We're going to talk a lot about leak channels, but basically there are a lot of, in neurons and muscle cells, there are a lot of these potassium leak channels, okay, that kind of operate in the background by pure diffusion, where they're just sort of doing their thing, you know, but they have an important physiologic role, which we'll talk about in a minute. So potassium is going down its concentration gradient. Okay, now, if you take the next logical step, where you had no potassium here, but now some has come over here, but it's still less than this, okay? What new situation is developing? What characteristic of this, besides a change in the concentration of potassium, is developing?
It's becoming negative, like negatively charged.
Exactly. The charges are changing, okay? And basically what's going on is the more potassium that comes over here, the more positive this side gets, and the more negative this side gets. And remember, that's what we said was the basic situation in a cell that's just kind of sitting there, that there are negative charges that accumulate around the plasma membrane inside the cell, and there are positives outside the cell. Okay? So this step right here is where you really get to see that there is a difference in charge now. So we have a difference in concentration with potassium, and we have a difference in charge across the membrane. So that brings our term electrochemical gradient back up that we talked about. This gradient is electrical and it's chemical, okay? And basically, this creation of this electrochemical gradient is the creation of the membrane potential, okay? This is how the membrane potential is created, the resting membrane potential is created in a neuron. Now, the next step that's represented by D, if you take that step one further, okay, that we're getting a change in charge, the more potassium that moves over here, okay, you're getting a greater charge of positive charge here. So now the positive charge in this area is repelling these positives from coming, more of them from coming. Okay, so it kind of favors the potassium staying on this side, and there's a balance, there's a give and take. Okay, so there's a concentration gradient initially. There's an electrical gradient, but the electrical gradient is also affected because you can only move so many positives into this compartment before they'll start repelling each other, right? Okay, so that back and forth happens until the system reaches equilibrium. Okay, so you have a concentration component, you have an electrical component, and you kind of have this secondary electrical component, and all of this goes on until the ions stop moving, and you have equilibrium. And that equilibrium is the equilibrium potential for that ion. Okay? More specifically, the equilibrium potential is the electrical force that is needed to balance the movement of ions that result from a concentration gradient. Okay? It'll make sense when you go over it again. But it's the electrical force needed. So here, in order to reach equilibrium with the concentration and the movement of the ions, there is an electrical force that develops to balance this movement. Okay? And that is what an equilibrium potential is. And you have a different equilibrium potential for every ion.
So what are those little backward arrows for the sodium mean?
That's showing that there's no movement of sodium, that we have isolated our discussion just to potassium, even though that doesn't happen in real life. So that the sodium channels are closed, that's what that means. So you still have the positive charges, you know, of the sodium over here to figure in.
So this is just equilibrium for potassium.
Right,
Not
right. So you have, and we won't do them all, but you know, you have sodium, you have chloride, you have magnesium, you have calcium. I mean, you know, it gets complicated, but I believe that's all I wanted to say on that. Okay, so this next one is basically the same, but it's for sodium. And just as a way to kind of review, and hit it home. We still have extracellular, intracellular compartments. We start with this manufactured fake situation of closed channels, exactly equal concentration, exactly equal valence and charges on either side. And then suddenly we pretend, okay, if we open sodium channels, what happens? Okay. Well, we know that sodium has its high concentration on the outside of the cell. So its concentration gradient will allow diffusion across or downhill, like we said, downhill into the intracellular compartment. The potassium channels in this example are closed. Okay? So sodium moves across. And there is a tendency, as this positive charge builds up in this compartment, there's a tendency for these positives to go back out, okay? Because remember, this is negative on the outside, so they're, you know, when it gets too positive on this side, then they start getting attracted to this negative, relatively negative side, okay? So, basically, you end up with the same situation, okay? The big point, the big difference between sodium and potassium is that there are fewer leak channels with sodium. There are fewer leak channels. So when we talk about the resting membrane potential of the whole neuron, it makes a difference. In other words, sodium and potassium, it's one of the reasons that sodium and potassium have unequal contributions to that electrical charge, is because of unequal leak channels. So the ions are not moving the same, okay, with regard to sodium and potassium. But essentially, the same thing happens, and this is in your book, as with the potassium, okay? Okay, so there is a very long, complicated discussion in the book with all this math. And again, we're not going to get that involved, but what I want to mention is that when it comes to membrane potentials, and again, membrane potentials are electrical forces, okay? So they're closely related to the Fick's equation where we were looking for net flux of ions, but that was concentration gradient, right? That was concentration. This takes into account the electrical component that we're looking at. So the Nernst equation is kind of the corollary to that Fick's idea, in the sense that how do things move across the membrane? How can we measure them and put it mathematically, you know, into terms that show us? And E is equilibrium potential. So E stands for equilibrium potential, and then the subscript is whatever ion we're looking at. So far we've looked at potassium and then sodium, okay? And I've already mentioned that it's in millivolts, okay? I've also told you that the equilibrium potential is that electrical force that's required to balance the difference in the concentration of the ions, right? So the Nernst equation tells us that we can figure the equilibrium potential for any ion if we use, and you're not going to have to write this equation, but you need to know what's related to what. And basically, 61 is a constant that takes into account gas, temperature, and electrical constants, okay? Z is the valence of the ion, okay? And then we have the concentration outside the cell over the concentration of the inside of the cell, okay? And the log of that difference, okay? So if you plug all those numbers in, all right, and again, just know the things that the Nernst takes into account. If you plug all that stuff in, what you end up with is the equilibrium potential for sodium is plus 60 millivolts, and the equilibrium potential for potassium is minus 90. Those numbers you have to know, okay? So, again, this would be if you had this situation, okay? And you were measuring sodium, okay? Then your voltmeter would say plus 60. And if you were measuring potassium, your voltmeter would say minus 90. The next statement is really kind of obvious. The greater the permeability to an ion, the greater the contribution that ion will make to the membrane potential. So in the case of sodium, you see that they can be quite different. Okay, that sodium is a positive 60, potassium is a minus 90. So when you start factoring all these other ions that I talked about, the more permeable the membrane is to the ion, the more it will diffuse, the greater the concentration gradient, and then the greater the electrical force that's required to offset that. And that's our membrane potential, okay? Your book also talks about the Goldman-Hodgkin-Katz equation, which is really complicated. You don't need to know that. I'm just boiling it down for you that all you need to know is that it's basically a fancy version of the Nernst equation, but it takes into account all the different ions, okay? So you can see here the Nernst equation would be just one ion, and that never happens. So if there's an equation for all the different ions, and you can plug all those numbers in and get an equilibrium potential, okay, that would represent more what is in nature. Okay, so we've kind of, this is a different way to look at it, but we've kind of seen this idea that resting membrane potential is due to a concentration gradient, and it's due to an electrical gradient. And like any vector, it's going to be influenced by magnitude and direction, okay? So this is a schematic to kind of show you, this is our neuron, and remember we said that there's a lot of sodium in the extracellular compartment, okay? So they put a big sodium here and a little sodium here, okay? And that's to remind you of that. So your concentration gradient is going to be in this direction, okay? Blue arrow is concentration. So sodium is going to tend, if channels are open, sodium is going to tend to want to move into the cell, okay? Also, electrically, because the equilibrium potential for sodium is plus 60, it's going to tend to want to move into the cell as well. Because remember that remember you can picture like all little negative charges right up that kind of aggregate right up against the plasma membrane. So it's going to tend to want to go from an area of positive charge to negative charge. Okay? So this is a summary of your sodium. Potassium is a little different. Again, the blue represents a concentration gradient, and we said most of our potassium is inside the cell. So they put a small k out here, and the potassium will tend to move outside the cell, and this is down its concentration gradient. Okay? Now, remember I said that happens when the channels are open. Obviously, you have to have the potassium or the sodium channels open for them to move across. And there are more, as I said before, there are more potassium leak channels than there are sodium. Okay? So what that means is there is a greater effect exerted by potassium than there is sodium. Remember I just said about the permeability of the ion will create a greater part of that equilibrium potential in the Nernst equation. So because these channels, and they're leak channels, which means they kind of stay open all the time. They're not ion gated, they're not specially controlled. So potassium tends to leak through them more than sodium. So our resting membrane potential for our neuron is closer to the potassium side. Potassium is having a greater effect. So we said the equilibrium potential for sodium is 60, positive 60, and we already said that when you plug in the numbers in the equation, the equilibrium potential for potassium is minus 90. Okay, those numbers you have to know, and you also need to know that at rest, when all of these forces settle down, what you end up with is minus 70, okay, which is the resting membrane potential of a neuron, minus 70 millivolts. And it's because this is due partly to sodium and partly to potassium, but more to potassium, more due to potassium.
You said negative 70 was a resting membrane potential for what?
The neuron. Okay, this is a duplicate of the sodium potassium ATPase pump, and I just wanted to remind you that on top of this physiologic phenomenon that establishes this resting membrane potential, okay, that where we're talking about concentration gradients and electrical gradients, but we're not talking about anything that's requiring use of energy. Okay, so on top of this, as a reminder, we have the sodium potassium ATPase pump, okay, which is using energy to move 3 sodiums out for every 2 sodiums that go in. Okay, so you can see how the sodium potassium ATPase pump takes a resting membrane potential and exaggerates it even more, because you're pumping out 3 positives for every 2 that you take in. So every time this conformation change occurs, you're getting more of a negative charge here. Okay? So you see how the negative charge can build up inside beyond what it was when we looked at it at a resting cell. Okay? Because now we have this extra feature that's using, this pump that's using energy. So that's kind of what this slide is trying to tie together for you, is that this is extracellular, this is intracellular. Again, the size of the type is supposed to remind you of the relative concentrations inside and outside. And you normally have, you normally have that slight negative charge that's right near inside the cell at the plasma membrane, and you have the relative positive charge outside that we've been talking about. And the basic resting membrane potential is established by the concentration gradient, and I'm repeating myself again, just by the concentration gradient, and then the potential itself is the electrical force that's required to offset that difference, okay? So you have basically a resting membrane potential. If this was a neuron and you didn't have a sodium-potassium pump going on, then it would be sitting there at -70, okay? But the sodium-potassium ATPase pump is also functioning, so for every 3 sodiums that are pumped out, only 2 potassiums are pumped in, so you're getting more and more negative, okay? And the other thing that's going on that affects all of this are the leak channels. This is supposed to show you that these are just leak channels that are open, and that there are some for sodium and some for potassium, but there are a lot more for potassium, okay? So those are just persistent leaks that kind of happen all the time, but it makes potassium have a greater effect, okay? Okay, so excitability. What we're building up to is, how does a neuron work? I mean, it's real easy to say, oh, there are electrical impulses that are traveling from one neuron to the next, but now you're at a point that you want to understand what's really happening at a molecular level. So in talking, basically I'm just going to define excitability. I have discovered that there are students that make it, or that are in this class, that have never taken an exam that was not a multiple choice exam. And as I said in the orientation, the department and the university has designated this a writing enriched course, okay? They want to make sure that you can write something that makes sense in the major subject that you're getting your degree in. So, but I still discovered that vocabulary was a sticking point, and that people were not really learning vocabulary, so they didn't really know how to use the words in a short essay answer, and they didn't always know what was being asked for, okay? So I actually have a whole section dedicated in the first part of the exam to vocabulary, okay? And it's a little, to me, it's a gimme, but people still struggle with it. So this obviously is a definition, so this could be on that first part, and all you gotta do is commit it to memory, okay? It's the ability to produce electrical signals that can transmit information between different regions of the membrane. That sounds pretty easy to understand. But when we start looking at the terminology that we're going to use, okay, we have time on this axis, and then we have the membrane potential in millivolts, okay? And we're talking about neurons, so the two ions that make the most contribution to the resting membrane potential of a neuron are sodium, we already said, at plus 60, and potassium at minus 90. And we've said that when these two have a chance to balance each other out, we end up with a resting membrane potential of minus 70. Okay? All right. So, depolarization. Okay? Depolarization, if you see a minus something, you would think, oh, well, that just goes minus to plus. You know, depolarization would go minus to plus. It's real important to think that what it is it's less negative. That's what depolarization is. Depolarization is in this direction, but it can be less negative. So a minus 40 still represents depolarization, even though you have not crossed over to the positive charges, positive nature of the charges, okay? And as a matter of fact, when you do cross zero, so in other words, this is kind of our baseline, this is kind of our zero, this is our baseline. When you do cross actual neutral electrical zero, it's called an overshoot. Okay, so this is an overshoot into positively charged territory. Okay? When a cell returns to its resting membrane potential, then it's called repolarizing. It's returning to the minus 70. Okay? In some situations, there can be an overshoot, okay? And you can have an even more polarized membrane than you would at resting. And that would be a hyperpolarization. Okay? Hyperpolarization. Okay? So all the terms are relative to resting membrane potential, which is minus 70. So we have basically two types of potentials. That, in other words, two situations where all of this results in some action, okay? One is a graded potential, the other one is the action potential, okay? So, what is a graded potential? It's a localized change in a membrane potential of variable amplitude and duration that is conducted decrementally, okay? And when we talk about action potentials, you'll be able to compare and contrast the two, and this will make a little more sense, okay? But the deal with graded potentials, if this is your nerve axon, is that they're conducted decrementally. So the further you go, the smaller they get, okay? And because the further from the site of initial depolarization, from the site of the initial electrical change, because the further you get the smaller they become. It's called localized, because they don't travel forever. They just travel short distances, okay? And also, the amplitude of the potential, okay, changes. So they get weaker and weaker. So this amplitude changes, okay? No threshold and no refractory period. We'll get to that later, okay? So let's stop there. We'll do this one more slide on graded potentials so you can kind of understand where the ions are